Alright, Assalamu alaikum. So in this video, inshallah, we'll be completing electrolysis of aqueous ionic compounds. We started off with electrolysis of aqueous ionic compound in the previous video and we did pretty much of it. This video is more of a completion of what we had started up in the previous video. So electrolysis of aqueous ionic compounds. Now, before we get into what's actually new in this video, let's very quickly recap what we studied in the previous video. So the first thing that we studied was that when an ionic compound is put in water, it dissociates into its ions. For example, if I have sodium chloride, that was the example I gave in the last class as well. Sodium chloride in an aqueous solution will break down into sodium ions and chloride ions. And I explained the reason behind it. The reason was that ionic compounds have kind of poles. Why? Because it's made up of a cation and an anion. And similarly, water molecules also have poles, with the oxygen atom being slightly negatively charged and the hydrogens being slightly positively charged. So when an ionic compound is put in water, what happens is that the water molecules orient themselves around the ionic compound such that the partially negatively charged oxygen molecules of the water molecules surround the sodium atom, sodium ion, sorry, and the partially positively charged hydrogen atoms of the water molecules surround the chloride ions. The partially negatively charged oxygen atoms pull the sodium towards themselves, and similar is the case with the partially positively charged hydrogen atoms which pull the chloride towards itself. This creates a tug of war kind of situation, and this tug of war situation is sufficient to break the electrostatic forces of attraction that hold sodium and chloride together, giving us free ions. And once the free ions are produced, water itself dissociates to form ions, and the ions that are released by water are hydrogen ions, H plus and OH minus. And therefore, in the previous video, I told you that for any ionic compound which is dissolved in water, the total number of ions in the solution is not going to be 2 as was the case in molten ionic compounds, but rather 4. Therefore, if we have, let's say, copper sulfate in an aqueous solution, we'll have copper ions and sulfate ions from the copper sulfate, and we'll have hydrogen ions and hydroxide ions from water. Similarly, if I have, let's say, calcium nitrate, it's going to give us Ca2 plus from and NO3 minus from the calcium nitrate salt itself, and H plus and OH minus from water. Now when electrolysis is performed, both the cations will move to the cathode and both the anions move to the anode. However, any one of the cations will be discharged and any one of the anions will be discharged. The remaining will stay in solution. And now comes the question that how will we decide which of the two from the cations and the anions will actually be discharged and which will remain in solution. So now we'll come to the criteria. We'll review the criteria. The first thing that I told you in the previous video was that the discharge is determined by two factors. The first factor is concentration of the solution. Concentration of the solution. And the second thing was the electrochemical series. Now, if we have an aqueous solution of any ionic compound, there are two possibilities. Aqueous solution. It'll either be dilute or it will be concentrated. A dilute solution is one which has proportionately more water than the solute, and therefore it will have a higher concentration of hydrogen ions and hydroxide ions than the ions coming from the ionic compound itself. On the other hand, a concentrated solution is the one which has a proportionately higher amount of ionic compound in it, or any solute to be more general. And therefore it will have more of the cations and anions coming from the ionic compound. So let's say that this was a concentrated solution of copper sulfate. So obviously it's going to be having a greater proportion of copper ions and sulfate ions as compared to hydrogen ions and hydroxide ions. Similarly, if this is a dilute solution of calcium nitrate, then we will be having a much greater amount of hydrogen ions and hydroxide ions as compared to the calcium ions and the nitrate ions. Now, the rule in the previous class that I told you about deciding the discharge was that the concentrated ion will be discharged. I'll just write the rule down again. The concentrated ion will be discharged if the gap between the competing ions in the electrochemical series is 3 or less than 3. If more than 3, that is, if the gap is more than 3, the ion lower in the series is discharged. Now, if you take a look at this law, I haven't mentioned about the nature of the gap. So we won't be concerned about it. What do I mean by the nature of the gap is that we don't care whether a substance is above or below. We just look at the gap and nothing else. So I'll just explain with these two examples here. If I'm electrolyzing dilute calcium nitrate, so the rule, according to the rule, the concentrated ion will be discharged if the gap between the competing ions is 3 or less than 3. Now, if we take a look at the electrochemical series for cations, we'll notice that the gap between calcium and hydrogen is much more than 3. Therefore, we come to the second clause. That is, if more than 3, the ion lower in the series is discharged. Therefore, hydrogen ion will be discharged at the cathode. Similarly, if we take a look at the anionic part of calcium nitrate, the rule again says that the concentrated ion will be discharged if the gap between the competing ions is 3 or more than 3 or less than 3, sorry. And exactly the same thing happens here. The gap between nitrate and hydroxide in the electrochemical series for anions. Remember the mnemonic that I told you in the last class. Faisal Sabzwari never cooks biryani in oil. Fluorides, most difficult to discharge, followed by sulfates, followed by nitrates, followed by chlorides, then bromides, then iodides, and then hydroxides. So we can see that the gap between nitrate ions and hydroxide ions in the electrochemical series is more than 3. And therefore, the second clause comes in, that is, the ion lower in the electrochemical series is discharged. And therefore, hydroxide ions will be discharged. Coming to electrolysis of concentrated copper sulfate. Now, concentrated copper sulfate means that we have proportionately greater amount of copper ions and sulfate ions in the solution. Now, copper is concentrated, and therefore, according to the rule, concentrated ion will be discharged if the gap between the competing ions in the electrochemical series is 3 or less than 3. And when we take a look at the electrochemical series for cations, we'll notice that the gap between copper and hydrogen in the electrochemical series is just 1. And even though copper is more difficult to discharge as compared to hydrogen, copper is easier to discharge as compared to hydrogen, copper is going to be discharged. Why? Because the gap was just 1. I'll take another example soon. FeCl2. This is concentrated FeCl2. We'll do this example after this. Yeah. And now let's take a look at the anionic side. In the anionic part, we see that sulfate is the concentrated ion, and if the gap between sulfates and hydroxides is 3 or less than 3, then sulfate should be discharged. However, the gap between sulfates is greater than 3. Between sulfates and hydroxides is greater than 3, with hydroxide being lower in the series. And therefore, the second clause of the law kicks in and hydroxide ions will be discharged despite not being concentrated. Now let's take a look at the electrolysis of concentrated iron chloride. The ions in solution are Fe2 plus, Cl minus, then we have H plus and OH minus. Now since it's a concentrated solution, we have a greater amount of iron ions and chloride ions. According to the rule, the concentrated ion will be discharged if the gap between the competing ions is 3 or less than 3. Now if we take a look at the cationic side, we notice that the gap between iron ions and hydrogen ions in the reactivity series is less than 3. Therefore, iron will be discharged. Despite the fact, regardless of the fact that hydrogen is easier to discharge. Why? Because hydrogen is lower, then it's in, then we have lead, and then we have hydrogen. Being lower in the electrochemical series means that it's easier to discharge hydrogen as compared to iron. But iron is more concentrated and the gap between iron and hydrogen is less. Therefore, despite the position of iron relative to hydrogen, iron will be discharged. Why? Because it's more concentrated and the gap between the competing ions is less than 3. Similarly, if we take a look here on the anionic side, chloride ions should be discharged if the gap between chloride ions and hydroxide ions in the electrochemical series is 3 or less than 3. And that's exactly what's going to happen. The gap between chlorides and hydroxides in the electrochemical series is exactly 3. And therefore, chloride ions will be discharged. Now let's come to making equations. And it's exactly the same thing as we had studied previously. So let's do something with, let's start with copper sulfate. Alright, a small reminder, I told this in the previous video as well, that in your CIE examinations, if the examiner says that we are performing electrolysis of an aqueous solution of maybe copper sulfate, then remember this, that aqueous refers to concentrated, and therefore you will treat the solution as a concentrated solution. Now, we are performing the electrolysis of dilute copper sulfate. So what happens at the cathode? Now please follow these steps. I find it very useful And if you have a strategy that you find useful, you are most welcome to use that. I'll do it with the strategy that I find useful. And you've seen this strategy, I'll just do the same thing again. So what happens is that at the cathode, we have both the copper ions and the hydrogen ions. Both travel to the cathode, but only one of those will be discharged. At the anode, we have sulfate ions and we have hydroxide ions. Now, since it's a dilute solution of copper sulfate, it means that we have a higher concentration of hydrogen ions and a higher concentration of hydroxide ions. You should make these arrows like I have done. Why? Because it really helps in identifying which is the concentrated ion, and it helps you frame your thinking procedure accordingly. Now, the rule was that a concentrated ion should be discharged if the gap between the competing ions is 3 or less than 3. Therefore, at the cathode, hydrogen ions will be discharged because the gap between copper ions and hydrogen ions in the electrochemical series is just 1. At the anode, what happens is that the hydroxide ions should be discharged if the gap between sulfate ions and hydroxide ions in the electrochemical series is 3 or less than 3. The gap between between the two competing ions here is more than 3, and therefore the second clause of our law kicks in, and the ion lower in the electrochemical series, that is the hydroxide ion, will be discharged. Now coming to the equations. The anodic equation. We'll always write the anodic equation first because the electrolysis reaction starts at the anode, and I have been telling this since our very first video on electrochemistry. Now, since the hydroxide ion will be discharged at the anode, our equation will start with hydroxide ions. Now, this is a very weird equation, and you'll have to memorize this equation because it's actually pretty weird. So it's 4OH minus. They are going to give us 2 molecules of water and oxygen and 4 electrons. Since it's an ionic equation, we'll write the state symbols. Aqueous, H2O is liquid, no? It's a pure substance. So we'll write liquid here and not aqueous. And oxygen is a gas, so sorry, so we'll write G here. Done. Now let's come to the cathodic side of the equation, of the reaction. So hydrogen ions will be moving to the cathode. Now hydrogen ions need to gain electrons and they'll form hydrogen. Now the thing is that hydrogen is a gas, and gases, except for noble gases, exist as diatomic molecules. Therefore, we'll add a 2 here, and therefore a 2 will be added here and another 2 here, and then come the state symbols finally. Gas. So now coming to the overall equation. For the overall equation, the rule was that we balance the electrons. For this reason, we'll have to multiply the cathodic equation by 2 so that we can get 4 electrons. And what happens is we have 4H plus 4E minus give us 2 molecules of hydrogen gas. Now the overall equation becomes, let's show some cancelling out here. We have 4OH and 4H plus. 4OH minus plus 4H plus gives us 2H2O plus O2 plus 2H2. The state symbols finally. Right. So now we'll come to the observations, which is a very important part of electrolysis. Now we can see that hydrogen ions were discharged. Hydroxide ions were discharged. What remains in solution is copper ions and sulfate ions. These remain in solution. Therefore, the first observation that we will see if we perform such an electrolysis is that the solution is going to become more concentrated. We know that the color of copper sulfate is blue. Therefore, as more and more hydrogens and hydroxides are lost, what will happen is that the blue color of the solution will become more prominent. The first observation is the solution becomes more concentrated. And how do we know this? Because the blue color becomes darker. The second thing, if we take a look at the cathode, a gas is being produced. If we look at the anode, a gas is being produced. So the second observation is gases produced at both the cathode and the anode. Now the third observation is a bit difficult to observe. In fact, it's not difficult to observe, it just requires a very keen eye. Let's take a look at the overall equation now. According to the overall equation, we have two molecules of hydrogen gas being produced for one molecule of oxygen gas. Therefore, the key here is that double the volume of hydrogen gas will be produced as compared to oxygen gas. So this is going to be a third observation. Double the volume of gas. Now since we don't know the identity of the gases, right? So we won't mention in the observations that which gas is being produced at which electrode. So I'll go in a very general terminology. So what I'm mentioning is double the volume of gas is produced at the cathode than at the anode. Right. Now let's repeat this electrolysis reaction. This time we'll be using not dilute but concentrated copper sulfate. And you will notice how things change. So now we have concentrated copper sulfate. So at the cathode we have copper ions and hydrogen ions. Copper ions coming from the salt and hydrogen ions coming from water. At the anode we have sulfate ions coming from the salt and hydroxide ions coming from water. And since it's a concentrated solution, we have proportionately greater amount of copper ions and sulfate ions as compared to the hydrogen ions and the hydroxide ions. Now, according to the rule, the concentrated ion will be discharged if the gap between the competing ions is 3 or less than 3. Therefore, copper will be discharged. Why? Because the gap between hydrogen and copper ions in the reactivity series or electrochemical series is just 1. And at the anode, sulfate ions should be discharged if the gap between the sulfate ions and the hydroxide ions is 3 or less. But because the gap between sulfate and hydroxide ions is greater than 3, the ion lower in the reactivity series will be discharged, and that is hydroxide. So now again, coming to our equations, the anodic equation will be featuring the hydroxide ions, that is 4OH minus releases 2 molecules of water plus 1 molecule of oxygen gas and 4 electrons, and here come our state symbols. What happens at the cathode is that it's copper ions that are moving, that are being discharged. So what happens is copper ions are in aqueous state, whereas the copper formed here would be a solid. So now we can make the overall equation. For the overall equation, we need to balance the number of electrons in both the anodic and the cathodic equations. For that, we need to multiply the cathodic equation by 2, which would give us 2Cu2 plus 4 electrons gives us 2 molecules, 2 atoms of copper. So if we now, sorry, this is a solid. So if we cancel out the electrons, we get our overall equation as 4OH minus plus 2Cu2 plus, this is aqueous, this is again aqueous, and this gives us 2H2O plus O2 plus 2Cu, liquid, gas and solid. All three states of matter are being produced here interestingly. So now let's come to the observations. Now the first observation would be regarding the ions that remain in solution. Since copper ions are discharged and hydroxide ions are discharged, hydrogen ions and sulfate ions remain in solution. And therefore, progressively the concentration of copper sulfate falls, which is manifested by drop in a decrease in the color intensity of the solution. So the first observation will be that the blue color of the solution fades. Blue color of what's happening? Of the solution fades. Second observation. Just notice here that as the reaction proceeds, there will be a decrease in the amount of hydroxide ions in the solution. Why? Because they are being broken down to produce water and oxygen. And therefore, a drop in OH minus means an increase in hydrogen ion concentration. And an increase in hydrogen ion concentration means that the solution is becoming more acidic in nature. So the second observation is that the electrolyte becomes more acidic. Becomes more acidic. And which acid will be formed, just by the way? You won't write this in your observation, but you can see here that hydrogen ions are remaining in solution, sulfate ions are remaining in solution, and therefore they should combine together and produce sulfuric acid. The third observation. Let's take a look at the anode. A gas is being produced. So we can say that a gas is produced at the anode. And sometimes it's really helpful if you write the test for that gas as well. So to be more complete, we can say a gas is produced at the anode. Since it's oxygen gas, we know the test for oxygen is that you bring a glowing splint near the end of a test tube suspected of containing oxygen. And if the gas is oxygen, the glowing splint will be rekindled. So a gas is produced at the anode which relights a glowing splint. A glowing splint. Right. Now let's take a look at the cathode. At the cathode, a solid is being produced, and that's copper. And therefore the observation at the cathode would be that deposits of a now copper, if you take a look at a copper wire, it has a slight pink tinge about it. And it's for this reason why your chemistry textbooks and CIE call the color of copper pink. So what you will see underneath the cathode is pink deposits of a substance which we know as a metal, and it's copper. So, and we mentioned the color of the deposit as well. So we'll say that pink deposits of a metal observed at the cathode. So these are the observations that you will see when you are electrolyzing concentrated copper sulfate. Now just take a look. When we had dilute copper sulfate, the observations were pretty different. The first observation is that the blue color became darker when we were electrolyzing dilute copper sulfate. However, it becomes diametrically opposite when we electrolyze concentrated copper sulfate. Why? Because the color of the solution becomes lighter in this case. Similarly, we see differences in the other observations as well. In electrolysis of dilute copper sulfate, gases were being produced at both the cathode and the anode, whereas this time a gas is being produced only at the anode, whereas we have a metallic deposit underneath the cathode. And since gases are not being produced at both the electrodes, uh, the volume of the gases produced is immaterial here. Now let's do one last electrolysis, and this time we'll be using an acid as an electrolyte. So let's do the electrolysis of aqueous hydrochloric acid. Now I use the term aqueous here, and I told you that aqueous refers to concentrated. So what happens at the cathode is that hydrogen ions from HCl and hydrogen ions from water both move to the cathode. Therefore, it doesn't matter which of the hydrogens we take, because obviously hydrogen is hydrogen. And then at the anode, we have chloride ions coming from hydrochloric acid, and we have hydroxide ions coming from what do you say? Coming from water. Since it's aqueous and aqueous refers to concentrated, therefore we have a higher concentration of hydrogen ions from the acid and higher concentration of chloride ions. Now, since the same ion from two different sources moving to the cathode, so it's actually just hydrogen that's being discharged at the cathode. And for the anode, however, we'll have to refer to the electrochemical series and a law. The law was that the chloride ion should be discharged if the gap between the chloride ions and the hydroxide ions in the electrochemical series for anions is 3 or less. And the gap between chloride ions and hydroxide ions is exactly 3. Therefore, chloride will be discharged. So now coming to our equations. The anodic equation would be Cl minus gives us Cl and an electron, which is obviously incorrect. Why? Because firstly, Cl exists as diatomic molecules. So there has to be Cl2 here, and to balance that we need 2 Cl minus and 2 electrons. Finally come the state symbols, that is Aq and gas. Then we come to hydrogen. H plus E gives us H, which again is incorrect. Why? Because we'll get H2 to balance that, 2H here and 2E here. So again, aqueous and gas. It's easy to construct an overall equation now. Why? Because electrons are already balanced. So the overall equation becomes 2Cl minus plus 2H plus gives us Cl2 plus H2. And here's a gas, here's a gas. Now what I want you to do is pause the video and think of the observations yourself, and then tally the observations with what I'm telling. So the first observation. Now remember, before we move on to the observations, we must identify which ions remain in solution. And here we can see that these are the ions that remain in solution. And Therefore, the first observation is that the solution becomes more dilute. Why? Because H plus and OH minus is actually water. Therefore, as the electrolysis proceeds, we have a greater proportion of water in the electrolyte. Hence, we can say that the solution becomes more dilute and hence less acidic. The first observation is the solution becomes more dilute and less acidic. The second observation, we can see that the gas is being produced at the anode as well as the cathode. So gases produced at the cathode and anode, and what's special is the volume of the gases. Both are being produced in equal volumes. Let's compare this with electrolysis of dilute copper sulfate, where we noticed that one molecule of oxygen was being produced as compared to two molecules of hydrogen, whereas here this is not the case. Here we have equal volumes of chloride, chlorine and hydrogen being produced. So we can say that gases produced at the anode and the cathode in equal volumes. So I hope that electrolysis of aqueous ionic compounds will be clear. If you have any questions, please feel free to comment in the comment section, and inshallah I'll try to get back to you in any other video, or maybe I'll respond to your comment in order to solve your query. Alright. Assalamu alaikum, jazakallah. In the next video, inshallah ta'ala, we'll be starting off with electrolysis using active electrodes. Till then, Assalamu alaikum wa rahmatullahi wa barakatuh.